Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Today we continue electronic circuit 1, and after midterm we will discuss two chapters, which is chapter 5 BJT AC Analysis, and then chapter 8 FET amplifier. Okay, and we already finished the chapter 1, chapter 2, chapter 3, this is chapter 5, not chapter 4. And we already finished chapter 1, chapter 2, chapter 3, chapter 4, chapter 6, and chapter 7. So after midterm, we will continue to finish our course in electronic circuit 1, this BJT AC analysis, and FET AC analysis or FET amplifier. Okay, so the first one is BJT AC analysis. Okay, so if you remember in DC analysis, actually we perform a DC analysis to get a DC component or to get a key point, the current quiescent currents. And in electronic circuit, we can use a BJT or FET as an amplifier. So we can amplify a signal from the input to the output, and the input can be decomposed into two separate components. There is a DC component or V1. We use a large V or big V here, and then small signal or AC component V1T or small v and small it. Why we use a t? Because of in AC component, the value, the magnitude of the AC component will be varies, depends on the t. So it's like AC is like this one, right? So this is the t and this is the magnitude, like a v or I, the voltage or current. So the magnitude of the voltage will be varies, like this one. This is large and then small, large, like this one. Depends on the T. But for the DC is fixed. Okay. So the DC is like this one. So this is the fixed one. So this is the DC. The blue one is DC, and the red one, this is the AC. Okay. And then the DC component signal is not a function of the time. So it's like a constant. It's like V1 is equal to 12 volt. And the V1T or small signal component or AC is function of the time. So the signal is an AC signal. The signal of VIT is referred as the small signal component because its magnitude generally small for all time of t. Okay. So this is the example. We have the input here. This is the input here. Okay, so this is the input and this is the output here. Okay, and this one okay, this one is amplifier. It's BJT amplifier. Okay, so this is the BJT amplifier. Okay, as amplifier, so this configuration can amplify the signal in input to the output. Okay, so the signal will go from, I use another like this one, to here, and then goes to the output like this one. So this is the AC signal amplified by this BJT amplifier, and then we control the operations of the BJT using the DC analysis. It's like how much we can amplify the signal. So we can control by using the DC component. We can change the key point, so the amplification characteristic of the BJT will be changed. Okay, so it's like we can see here, this is the input signal here in the base terminal IB, and then this is the output signal in the collector. We can see that this is the amplification, because this is the magnitude of IB is lower than magnitude of the IC. And then this also we can see from the magnitude of the voltage. This is the VB here, and then this is the VCE or VCQ. So the magnitude also larger after we amplify in the BJT. Okay. So as I mentioned before, the purpose of DC analysis is to establish a key point or quiescence point of our DC operation point. Okay, so the goal is to set the key point such that it does not go into saturation or cut off when an IC signal is applied. Because if we want to amplify a signal, we have to put the BJT in the linear region, not in saturation or not in cut off. So we have to carefully select the key point in the linear regions. And saturation and cutoff is useful for the switch, but not for the amplifier. Okay. Okay. If the key point in active region or in linear region, active region we call another is linear region, the transistor can operate as an amplifier. Okay, and then the purpose of AC signal is to obtain the gain, the ratio of the output voltage and the input voltage. So the gain here is the ratio of the output voltage and input voltage. To obtain the current and voltage gain, AI and VI, and also the input impedance and then the output impedance. Okay, so the AI is current gain, VI is voltage gain, the ratio of the output voltage and input voltage, and current gain is ratio of output current and input current. Input impedance is the impedance of the input, and output impedance is impedance of the output. Why this is we have to calculate the input and output impedance? Because we have to clarify that the amplifier is, because the amplifier will be connected to another device. So the input and output impedance is very important to connect to other device. So for example, we have the mixer here. Okay, and then after mixer, we have the power amplifier here, and then our amplifier, and then we have the antenna here. So the input impedance here, the I, and then the output impedance here, okay, will be connected to another device like a mixer and an antenna. And the input and output impedance should be matched to another block, to mixer and then to antenna. Mixer has the output impedance and antenna has the input impedance. The input impedance of power amplifier or amplifier here must be matched with the output impedance of the mixer. And then the output impedance of the power amplifier here should be matched with the input impedance of the antenna. Why it should be matched? Because of if the input and the impedance didn't match, the power cannot deliver effectively. So the impedance matching is very useful to deliver power. So all the power will be delivered to the circuit block. But if the impedance didn't match, so there is a loss. So it means that the T1 ZO of mixer must be matching with the Zin of power amplifier. This is the conjugate match, must be conjugate match with the input impedance of the amplifier. So the power loss will be decreased. So it means that like this one. So the power is coming from the mixer to the antenna Like this is the power we deliver. So if mixer and power amplifier is matched, so the power will deliver 100%, and then from power amplifier delivered to antenna. If the output impedance of power amplifier match with the conjugate match with the input impedance of the antenna, power will be delivered 100%. But if the impedance matching cannot perform well in this circuits block, the power will be lost in the connection. It's like here is the loss power and this is lost power. So it's very important to make the impedance matching between the circuits blocks in the system. Okay, so we can analyze the BJT AC analysis by adopting simple circuit model or transistor equivalent model. So this is how to perform the BJT AC analysis. The first one, we have to determine the key point here. Okay, so for example, yeah, whatever configuration. So the first one, we have to determine the key point. So how to determine the key point, you have to remember the DC analysis in the BJT. The first one, we have to looking for the intersection between the load line, the black line. This is the load line with the x-axis, and the intersection between the load line, the y-axis. And using this, if we use this configuration, a voltage divider configuration like this one, so the VCA is VCC minus IC multiplied by RC plus RE. So VCE cutoff is equivalent to VCC. If the IC is equal to 0 here, if IC equal to 0, like in here, so this is the VCC. And then when VCE is equal to 0 here, this is the VCC equal to 0, the IC saturation is the VCC per RC plus RE. So we got 2 points here in the intersection, and then we connect to bus point here. So we got that key point here. Yeah, we can choose what's the key point we want to use. It's like here or here or here or here. Yeah, but it depends on and the key point is depends on the function. I mean that maybe after this electronic circuit 1, you will study about the power amplifier. Okay, the power amplifier is the kind of the amplifier, kind of the amplifier that we use in the communications. So the power amplifier has many types. It's like a power amplifier type A, type B, type C. It depends on the key point. So it's like here. Here is the power amplifier type A. And if we put here, the key point here, so this is the power amplifier type B. And and here is type A. And between the type A and type B, this is like here is type AB. And then below of key point type B is type C here. So this is the type C. Okay, so depends on what kind of amplifier that we will design. But for for uh, for the beginning, actually in the book we will use the amplifier type A, like this one, in the center of the circuit characteristic. Okay, and then after we determine the key point, then we do as analysis by using the first one. We have to sort all capacitor here. We have the coupling capacitor here, and then we have the bypass capacitor here. And the coupling capacitor is used to prevent the DC currents coming to the input and coming to the output. It's like the open for the DC and then short for AC. So this is the C1 and C2 is coupling capacitor. So this is the short for AC and open for DC. This is what C1 and C2. So we have to carefully selected the value of the coupling capacitor. Larger is better. Larger capacitance is better. Okay. So the DC current will isolate in the circuit. Okay, like this is the DC. If we didn't put the coupling capacitor, the DC component, DC current will go to the input like this one, and we don't want like this one. Okay, so we use the coupling capacitor, and then C3 here is this is a DC bypass capacitor. So DC bypass capacitor is useful in AC and in DC. In DC, this is also short for AC and open for the DC. And if you remember, the function of the emitter resistor here is to make a stabilization in the DC analysis. So maybe you remember, if we put the emitter resistor here, if we change the beta of the transistor, the current, the IC, the collector current will change a little. But if we didn't put the emitter resistor here, if we change the beta, so the collector current will change drastically, will be changed larger. So we put the emitter resistor here to stabilize the collector current if there is a if the beta is changing, if the beta is changed. But in AC we didn't need a emitter resistor. Why? Because of the gain of the BJT is determined by output per input. So the input is the RE. RE is the emitter resistor, intrinsic emitter resistor plus emitter resistor here. Okay, so if we increase the value of this one, so the gain of AC gain will be decreased. So we have to remove this one. But emitter resistor is very useful in DC. So we put the parallel connection of the bypass capacitor. So if we perform the AC analysis, if we perform the AC analysis here, so the emitter resistor will be neglected, and we didn't calculate the gain using the emitter resistor because of we use the bypass capacitor in AC analysis here, so we can neglect this one, ignore the emitter resistor. Okay. So after we short the all circuit and open circuit all DC supply and ground them like this one. So it become like this one. So C1, C2, and C3 is removed, and then this is a short. Okay, the emitter resistor is ignored, and then VCC is changed to the ground like this one. Okay, and then we can we can draw this transistor for the small signal AC analysis, and we can redraw this configuration using this configuration. Okay, so this is the transistor, and this is the this one R1 parallel to R2, and then this is the RC. Okay, like this one. And the BJT is replaced by the equivalent circuit, and two transistor equivalent model will be introduced here. This one is RE transistor model, and then the hybrid equivalent V model. And then BJT are basically current control device. This one is our RE transistor model. Okay, so the RE model use a diode and current source to duplicate the behavior of the transistor. So it's like this is the BJT, this is the emitter, this is the base, and this is the collector. And then we can use the RE model. This is the diode here, and then this is the current source to duplicate the behavior of transistor. IC is equivalent to alpha to IE, and this is the IC. That is the IE. And one disadvantage of this model is sensitivity to the DC level. So this model is designed for specific circuit condition. It's like for the lower frequency. And then another model is hybrid V. Hybrid V is most useful for analysis the high frequency transistor amplifications. Okay, so in the lower, the hybrid V model is close to the RE parameter. So we can use the RE parameter for the lower frequency. And this is the hybrid equivalent model. We have the H1, this is the input resistance, and then HR is reverse transfer voltage ratio. HR is V1 per VO, and then HF is forward transfer current ratio, IO per IE here, and then HO is output conductance. So we can see here, there is no input impedance here, and then output impedance. But for the hybrid equivalent model, we put the input resistance and output conductance here. So this is the complete model for the BJT. And then this is the specified general H parameter model. We have the H1 input resistance here, and then HF or forward transfer current ratio, IO per I1. And then if we compare two model, the first one, this one is the H parameter model or hybrid V. HIE is equal to beta RE for the common emitter, and HFE is equal to beta AC. So yeah, actually we can this is the for H parameter, and then this is for RA parameter. And then for the common base, HIB is the RE here, and then HFB is minus A or minus 1. Okay, minus on IE. And this one is common emitter fixed bias configuration for the first. The input is applied to the base. This is the common emitter, and then the output from the collector. And then for the emitter bias, the high input impedance and low output impedance. And we have the high voltage and current gain here, and then passive between input and output is 180 degrees. So this is the characteristic of fixed bias. Okay, so this is for the homework. Okay, I will assign the homework in a mass again. Okay, I think for the first video, this all for the first discussion of the BJT AC analysis. Thank you very much for the attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.